Hey folks, Mr. G here again. Today what we're going to look at is an introduction into the capacitor. So capacitor is a different component that we're bringing into our course. It is something that is different from the resistors that we've been looking at so far. So the capacitor, chapter 12 is based on the capacitor. So again, that comes from our textbook. So, Principles of Electric Circuits, Conventional Current Flow from Floyd and Bakla. Okay, so chapter 12 is on the capacitor. What we're responsible for in this course is from section 1 to 5. So what I'm going to do is I'm going to try and give you a quick overview of the capacitor, its measurements, things like that, how to use it in a circuit, how to calculate things, and we'll take it from there. So here we go. The capacitor. The capacitor actually comes in many different styles. So I have a few of them here in front of me. You'll notice that there are some bigger, some smaller, some really small. Okay, they come in different physical size. We'll talk about what the size represents in a couple of minutes. But basically, this is what a capacitor looks like, or this is what a capacitor looks like. These are the two main styles that you get of capacitors. So what is a capacitor and what does it do? Well, a capacitor is actually made up of two conductive plates that are separated by an insulating material. That insulating material is what we call a dielectric. So we have two conductive plates separated by an insulating material. The material is what we call a dielectric. The job of a capacitor is to store charge. So think of it as a very small battery. It stores charge for use later on or for whatever the purpose may be. So again, the construction, two conductive plates separated by an insulating material. That insulating material is what's referred to as a dielectric. And what a capacitor does in general is to store small amounts of charge. So that's a capacitor in its general form. The unit is the capacitance of a capacitor. So capacitance is the amount of charge that is stored per volt across the plates. So a measure of capacitance is charge over the voltage, and that's voltage on the plates, so per volt. So if you remember from early discussions in our course, unit of charge is what's referred to as a coulomb. A coulomb is 6.24 times 10 to the 18th electrons that are all grouped together. So a coulomb of charge per volt is a measure of capacitance. So the unit is called the farad. So the unit of capacitance is called the farad. 1 farad is equal to 1 coulomb of charge placed across 1 volt on the plates of the capacitor. So if we have 1 coulomb of charge per volt, or on a volt across the plates, that is referred to as 1 farad of charge. So there are many types of capacitors, as you can see from this little display that I have here. The capacitors themselves come in two main types. The first one is called the electrolytic capacitor. The electrolytic capacitor, the symbol typically looks like this. Sometimes the plus is there, sometimes it's not, sometimes it's just the two lines. The electrolytic capacitor has a positive side and a negative side. So this has a polarity. And then we have a non-polarized capacitor. So if we looked at an example, that is an electrolytic capacitor. It has polarity. This is a regular capacitor without any kind of polarity. If you actually looked at this capacitor right here, you'll see that there's actually a black line with some arrows and a negative symbol that are pointing in this direction. So that means that this lead over here on this side is the negative lead. This is the positive. So if I looked at that, it would go like this in my circuit. So sometimes you will also find an indentation on one side, and the indentation is the plus. So somewhere the capacitors will be marked. Another example is this one here, where the negative side is actually marked down here. So this would be the negative side of the capacitor, so this one would go in like that. This capacitor, having no polarity at all, can go in either way, doesn't matter. Okay, so we have electrolytic, and we have ones with no polarity at all. Just a little side note, when you have leads coming out of both ends, this is called an axial component. When you have leads coming out of just one end, this is called a radial component. So this is an axial, this is a radial component. There are many different types of capacitors as far as the construction goes, and there's a few of them that are listed in the book in chapter 12, so you can go ahead and take a look if you like. Basically, it's the construction of the capacitor. What is the dielectric made of? That kind of a thing. The construction differs based on different capacitor types. Now, what does the physical size have to do with it? You'll notice here we have a big one, we have a smaller one, oh look, there's a smaller one even, and an even bigger one. These are all electrolytic capacitors. But what does the physical size have to do with it? Well, any capacitor has the capacitance value, so how much storage, so how much charge storage, and voltage. So the voltage rating of a capacitor figures out how much voltage you can actually put across a capacitor and have it store that value. It's typically a DC value. So from one end to the other end of the capacitor, how much voltage can I put across this capacitor? So when I'm storing energy inside, what is the maximum value of voltage that I could put across this capacitor? The other thing is the actual capacitance. The amount of storage space, if you will. So not only the voltage, but also the amount of charge. So typically the larger the voltage is, larger the plates, the larger the capacitor. The storage, the larger the capacitance, the larger the plates, the larger the storage. So if I looked at this capacitor here, this is 470 microfarads at 50 volts. So that means the largest amount of voltage I could put across here is 50 volts. It will store this much charge. When I look at this one, this is a larger capacitor, physically larger, but only 22 microfarads, but 450 volts. Okay, so in this case, this one is bigger because we have bigger voltage. Much smaller storage capacity, but bigger voltage. Now if I go to this guy down here, it is physically smaller, but it has 100 microfarads and 35 volts. So 100 microfarads is more storage than this, but the voltage is quite a bit less, 35 volts. So the two different values, the capacitance value and the voltage value, have an effect on the physical size of the capacitor. So, having a capacitor in a circuit. So I have a capacitor in a circuit. Let's pretend that this capacitor is 100 microfarads. So if I looked at the total capacitance from this point A to this point B, if I looked at the total capacitance, what I would see would be 100 microfarads. Now we all know from our studies in previous lessons that if we have resistors, what happens if we have two or more resistors in a circuit? How does that affect the total resistance of the circuit? Well, obviously, the same thing must apply for capacitors. So, if we add more capacitors in our circuit, what happens to the total capacitance of our circuit? Now, we know from our study on resistors that if we place resistors in parallel, the total resistance of the circuit goes down for every resistor we add. And we know that from previous discussions, R total of a circuit is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc., etc., etc. for a parallel circuit. In capacitors, that's not true. In capacitors, the total capacitance of a circuit is actually equal to C1 plus C2 plus C3, etc., etc., etc. So when in parallel, we add up the capacitance. Now, where have we seen this before? This is how we figure out total resistance of a series circuit. So we actually use the series resistive formula for parallel capacitors. So what we've got here is how we calculate our total of parallel resistors. Here is how we calculate C total of parallel capacitors. So in this example, this would be 100 microfarads plus 100 microfarads plus 100 microfarads, giving us a total of 300 microfarads. So C total for this circuit would be 300 microfarads. But what happens if we put capacitors in series? So now if we want C total of this circuit, so we got C1, C2, C3, and I'm going to say, just for fun, these are 75 microfarads, 75 microfarads, 75 microfarads. I want to look at C total of that circuit. If we looked at resistors in series, we know resistors in series is R1 plus R2 plus R3, etc., etc., etc. We know that resistors in parallel, this is our formula, but we just talked about the capacitors in parallel giving us this formula. So what formula do you think will work for capacitors in series? So if this is the capacitors in series, or sorry, resistors in series, the capacitor in series is going to be the 1 over C1 plus 1 over C2 plus 1 over C3, etc., etc., etc. So this actually works out to be, if you do the math, 25 microfarads as a total capacitance of this circuit. So we actually use for parallel capacitors, we add them up like we do resistors. For series capacitors, we use the 1 over formula to calculate the value. So when we have series capacitors, again, we use the 1 over formula. Parallel capacitors, we add them up like we do resistors. Now, we know that there are a couple of shortcut versions. So if we only had 2 capacitors, our formula is C total is product over sum. If we had any number of capacitors, the same value, you take the value of 1 and divide by the number of capacitors you have. So in this case, all these values were the same, and there's 3 of them, so 75 microfarads divided by 3 gave me 25 microfarads. So these shortcut formulas work for capacitors just like they work for resistors in parallel. So what happens now if we have a combination? Oops, that's not what we're looking for. We are looking for capacitors. There we go. And we wanted C total. So I'm going to make this 100 microfarads. This one's going to be 100 microfarads. This one here I'm going to make 50 microfarads. And this one I'm going to make 100 microfarads. Now, if we looked at trying to figure out what the total capacitance of this circuit is, we have to analyze this the same way that we would analyze a complex circuit with resistors in it. So what this works out to be is I've got 2 here in series. So in series, I got these formulas. I have 2 of them at 100. Same value divided by the number I got. So this here equates to a 50 microfarad capacitor. Then we have a 50 microfarad capacitor in parallel with another 50 microfarad capacitor. that is going to give me, so you got add them together. So when we do capacitors in parallel, we add them. So this will give me 50 plus 50 equals 100 microfarads. So this whole thing here equates to 100 microfarads. Then I have 100 microfarads in series with 100 microfarads. So I got 100 microfarads in series with 100 microfarads. So now I've got to do my in series calculations. I just happen to have, again, same value, two of them. So I got two 100s. So the total capacitance of this circuit is 50 microfarads. So again, we're solving this, splitting it in. We end up with one capacitor. That one capacitor is going to be 50 microfarads. Then I have a 50 and a 50 in parallel, giving me 100. Then I have 100 and 100 in series, giving me 50 microfarad total. So when you're working out these circuits, you work them exactly the same as if you would work a complex circuit of resistors. Only difference is that you must use the opposite formulas. So if you're calculating in parallel, you add them. If you are calculating in series, you must use one of these formulas. Okay? So series, again, you use one of these formulas. In parallel, you add them. And you can work your way through any complex capacitor circuit. All right. So now what happens when you place capacitors in a DC circuit? So this is where we go into chapter 12-5 again of our textbook. So 12-5, we're going to look at what happens in that capacitor when we apply this in a DC world. Okay, so capacitors in a DC world. So what's going to happen? All right, let's take a look. Okay, so capacitors in DC. So, mentioned a few minutes ago that basically a capacitor is a small type of battery, if you will. It charges up like a battery would charge, and it stores that charge. So if I take a DC power supply and I feed through a resistor into a capacitor, and we will make an electrolytic type capacitor by putting the plus sign there. We have a resistor, we have a capacitor, and let's say we have 10 volts of voltage coming from our supply. So basically, just like everything else in the world, nothing happens instantaneous. It takes time for the capacitor to charge. So think of it as the electrons are leaving the power supply, flowing through the resistor, and building up charge inside that capacitor. What is the job of a resistor in electronics? The job of a resistor, if you remember, is to limit the current flow. So that there's not a huge rush of current, this resistor kind of keeps everything under control. And then we're going to basically charge up the capacitor. Once the capacitor charges to approximately 10 volts, which is what this value is here, the current stops flowing. So once the capacitor charges all the way up, and this side equals this side, then there is no more current flowing. So how fast does this all happen? How fast does the capacitor charge? Well, that relies on two different things. The first one is obvious, the resistor. The resistor actually limits the amount of current, how much current can flow through that wire at any given time. The second one is the capacitance, the storage capability of that capacitor. The larger the capacitance value, the bigger the bucket, if you will, that holds the electrons. The smaller the capacitance value, the smaller the bucket. So a bigger capacitor will take longer to fill up than a smaller capacitor. So what we have is R, so the resistance has a factor, and the capacitance plays a factor in how we actually charge up, or how much time it takes to fill this bucket. R times C is what's known as tau. Tau is a time constant. So R times C is equal to 1 tau, one time constant. To charge up a capacitor, to go from 0 to full charge, takes 5 tau. So 5 tau to fully charge the capacitor. So if we looked at, let's say, here is a gas gauge on your car, and you got empty over here, and you got full over there, and you got your little needle. If you are filling up your tank at the pump, you've got two things that determine how long it takes to go from empty to full. The first one is the flow of the fuel into the tank. That's your resistance. So the size of your hose that comes from the gas pump, the size of your hose is the restrictive part. If you had a bigger hose, you would fill faster. If you have a smaller hose, it takes more time to fill. So the resistance is what limits the current to fill up the capacitor. Physical size of your hose limits the flow of fuel to fill up your tank. The other thing is, how big is your tank? If you have a very large tank in your vehicle, it's going to take longer to fill up with the same hose than if it was a smaller tank. Same thing here. Larger capacitor will take longer to charge if you have the same resistor. Smaller capacitor will take less time to charge. So the idea is to go from empty to full takes a certain amount of time. How much time? For a capacitor, it's a value of 5 times tau. So whatever this value of tau is, and tau is based on the resistor and the capacitor, whatever that value of tau is, 5 times tau will take you to a full tank of gas or a full capacitor. So what does that actually look like? The capacitor does not charge perfectly linear. the capacitor actually charges on a curve. So if this is my voltage on the capacitor, and this is my time, my time will be divided into time constants. 1 tau, 2 tau, 3, 4, 5. Again, tau is a measurement in seconds, and it's based upon the R value and the C value. So, we know that full charge pretty much will happen at 5 tau. So we'll just go here, 4 tau, 3 tau, 2 tau, 1 tau. So we know that full charge will happen here. So that's actually about 99% full charge value. What we have is a curve that looks like this for charge. After 1 tau, we are 63% charged. 2 tau, we are 86% full charge. After 3 tau, 95%. After 4 tau, 98%. And then after 5 tau, 99% charge, and that is considered full charge. So our capacitor does not charge instantly. Our capacitor charges over time, and it follows this curve. So after 1 tau, we've charged up to 63%. 2 tau, we've charged up to 86. 3 tau, 95. 4 tau, 98. And after 5 tau, we are at 99% charge. So what we're going to do is take a look at how we discharge the capacitor. Okay, so now what about discharging the capacitor? Well, let's pretend we have a capacitor now. Here's a capacitor in the circuit. That capacitor is going to discharge through a resistor. So after we have charged it up, we are now going to discharge. So the capacitor and the resistor, and now the capacitor is going to drain through the resistor. The question becomes, how fast does the capacitor drain? Well, the capacitor draining, it relies on two different things. One is how big is the capacitor? The larger the capacitor takes more time to drain. The second is the value of the resistance that it's draining through. So again, the capacitance, so the size of the capacitor, the resistance that it's actually draining through is equal to tau. So, how long do you figure it's going to take to fully discharge the capacitor? Well, 5 tau. To go from full to 0 volts. So if you have a fully charged capacitor and you're going to discharge through a resistor, it's going to take you 5 time constants in order to get down to 0 volts. Now we know from just a minute ago, here we go, The charging of the capacitor looks like this. So, the charging of the capacitor is not linear. After 1 tau, we have charged to 63, 2 tau, 86, 3 tau, 95, 4 tau, 98, 5 tau at 99. So, what do you think the discharge curve will look like for that same capacitor? Believe it or not, if I was able to flip that over, and I will just redraw these lines for you. More or less. So this is 1 tau, 2 tau, 3, 4, and 5 tau. After 1 tau of discharge, there is actually 37% left. After 2 tau, we are down to 86, so we got down to 14%. 3 tau, we are down to 5%. 4 tau, we are down to 2%. And in 5 tau, we are down to 1% remaining. So do you see where I got those numbers? Look over here. Flip that over. 63 and 37 equals 100%. 86, 14, 100%. 95, 5. 98, 2. 99, 1. They are the mirror opposites of each other. So the capacitor itself will go from full charge to 0 in 5 tau in a curve that looks this. It's the exact opposite of the charge curve. So the charge curve, after 1 tau, 63% charged. After 2 tau, we have lost 63% of our charge. What is left? 37. At 2 tau, we have charged up to 86. 2 tau, we have lost 86. What's left? 14. 95, 3 tau, we've charged to 95. After 3 tau, we've lost 95. What remains is 5. 4 tau, we've charged to 98. 4 tau, we've lost 98. Down to 2. 5 tau, we're charged to 99%. 5 tau, we've lost 99. And what we have left is 1% charge. So that's what it looks like to charge and discharge a capacitor in a circuit. So again, here's the discharge. So the capacitor becomes the supply and powers up for current through the resistor. And then here is the charge. So some kind of extra supply is charging up the capacitor through a resistor. Here, the capacitor becomes the supply of electricity and it discharges through the resistor. Could be the same resistor, could be a different resistor, could be a group of resistors, doesn't matter. Charging through the resistor charges up the capacitor. Discharging, the capacitor becomes the source of the electrons and it discharges through that resistor. Again, what matters is the resistance and the size of the capacitor, so the storage capability. What matters here is the resistance and the size of the capacitor, the storage capabilities. So that's where you end up with the size of the capacitor and the storage capability, size of the capacitor and the storage capability. Okay, and then it takes 5 tau in order to completely charge or completely discharge the capacitor. So, capacitors in DC, the charging and the discharging, you can find that little bit of a review, if you will, from chapter 12-5 of our book, and again, textbook. So the basic capacitor, you will find all the information that you need to know in chapter 12, right from the beginning through to storage, the types of capacitors, the voltage ratings, all the things that I talked about, series, parallel combinations, caps in DC, charging and discharging, all can be found in chapter 12 from sections 1 through 5. Okay, so chapter 12, section 1 through 5 in our course textbook. You'll be able to find out more information on the capacitor. Well, I hope this helps. Everybody take care, and we'll see you again next time.